Good afternoon. So, before we start today, how many of you are not happy with the current group assignment that you have for your projects? Are you happy with your current group? Because I had some complaints like where students wanted to change. No? Everyone is fine? Okay. But if you still want to switch groups, let me know. I can try to see what I can do. But if not, then you need to get going with your project. You need to start your project because the presentations, project progress presentations are coming, right? That's after the midterm, right? Yeah. So you need to get going. Okay. So in the last class, we started with logistic regression. And we said logistic function looks something like this, right? Logistic function looks something like this. And this is 0. This is your y. This is your x. So if x is positive, the value is around 1. And if it is less than 0, the value converges to 0. Right? And the function that does this, and they call it z here. So let's start with z. So the function is essentially function of z is equals to 1 divided by 1 plus e to the power minus z. Right? So if you have z as a high positive value, then this term goes to 0. This term goes to 0. 1 by 1 is 1. So that's what you see on the positive side. And if it is negative, the higher the value is, it becomes a very large positive number. And then 1 divided by a large positive number goes to 0. That's the logistic function, logit function, right? Here it is. And there is some linear portion here where it behaves like a linear function. And there are ways to tweak this region so that that region is minimal, so that you have exactly like a binary decision 1 and 0. Things are a little uncertain around z equals to 0. And for logistic regression, what we said is this z is equals to essentially a linear transformation of weights and the feature values. So this is I equals to 1 to d, let's say. So, and let's call it n actually to denote, no, actually this should be d because this is the dimension of the point, right? So, the question is, have we seen this term before? Where?
Perceptron.
Have we seen this in perceptron? We have seen this, right? What is this actually? Adding vectors.
It's the dot product.
It's the dot product, right? It's the dot product between the w and x. So essentially that dot product, and we used to make a decision on perceptron with this dot product. How? What did we do?
Whether or not it's greater than or equal to 0.
When it is greater than or equals to 0, what is the label? Positive. Otherwise, negative, right? That's what we did for perceptron. So now we have this same dot product here. We are just saying, we are just calling this dot product Z, and we are taking a logit transformation of that Z. So now the question is, why do this? It looks like very similar to perceptron, right? I mean, in perceptron, you could again do the dot product, take a decision. Then what is the point of this? Or what was wrong with perceptron that we want this? Yes?
Perceptron assumes, well, for good performance of perceptron, you need linear separable data.
Okay? How does this solve this? Yes?
Is it that it's like differentiable?
It is differentiable, for example, right? Yeah, that's true. But why do we want to differentiate?
To find the minimum? I don't know.
Find the minimum. Why?
Seems like that's usually a good thing to do.
Minimum of what? What is the point of finding a minimum or maximum? Why do we even bother about it?
That's where the slope is 0?
To find where the slope is 0. Yes, but slope of what? Why does that matter to us in this case? Okay, first of all, tell me how this number is bounded. What is the maximum value this function can take? 1. What is the minimum value? 0. How does it sound?
Probability.
Probability. Now you can treat this number as a probability and plug in all the formula that probability theory has. That's nice, right? Now you can apply optimization techniques based on probability theory also on this function. That is nice. For perceptron, if you have just one perceptron and you are training based on this formula and updating the weights, but if you have two perceptron connected, that's the kind of neural network style, right? Each node you see, like unit you see in a neural network, is essentially a perceptron. But the basic perceptron we have learned. Now, if you want to learn the parameter of two different perceptrons connected, how do you learn it? In other words, you cannot compute a gradient that you can backpropagate using a formula that uses if-else. If this is greater than 0, do this, positive, else negative. You cannot compute a gradient of if-else. Can you? So when you build a large network with perceptrons, you cannot do backpropagation as well. You cannot do gradients. And the number you get as a dot product is not bounded. Here, you get a bounded number between 0 to 1 that you can treat as a probability. And then you can apply all the properties of probability theory on this function. And also, for logistic regression, you have seen that this is how many mistakes you have to make before you converge. Now, if you have a point that is like super at the farthest corner, right, then the number of mistakes will increase quadratically. You have to make. So one single point, one outlier could make your algorithm kind of crazy to figure out the right one. So it's very sensitive to the outliers. So all these problems can be resolved if we transform this dot product into some kind of probability. That solves a lot of problems for us. And you will immediately see, like as we move forward, it will make our life a lot easier. So logistic regression is nothing but a perceptron with a logit function. It is a perceptron. But it's not the basic version of it where you do dot product and if and else. Rather, you do a transformation, a simple transformation to make it a probability. And that helps you apply probabilistic theories, optimization, compute gradients, likelihood, all those, even Bayesians on them. All right? So that's why we want to do this. Okay, so now the question is, you remember that thing that people were saying, we want to find a place where the slope is 0, or the maximum or minimum of something. What is that something? What is the something that we want to maximize or minimize? Yes? A cost function, okay. What is a cost?
And I guess there's different definitions we could use.
Different definitions, okay. Because now we have converted something into probability. Let's talk about a cost function that connects to probability. What is an ideal thing that I would like to, so think about this whole learning process. You want to learn, okay, first of all, tell me in logistic regression, what do you want to learn? What is our goal to learn? Yes?
The decision boundary, or
What is that?
which values should be positive, which should be negative? Or
What is the notation for that? What we are learning, the decision boundary. Which one denotes the decision boundary?
W.
W, right? W is what defines your decision boundary, and that is exactly what? Perpendicular to the decision boundary, right? That is W. Remember? And that's what we don't know. In perceptron, we were learning W by saying Wt plus 1 equals to Wt minus x, plus x, and Wt1 is equals to Wt minus x. This one was for positive error, and this one was for negative error, right? That's how we learned. We went through one example at a time, and we updated W until we found a plane that separates. That was our learning algorithm, right? But now, with this transformation, what should be our update rule or learning algorithm? That's the question, right? So we want to learn W, but what kind of W? Now try to connect with, you said something you want to maximize, minimize. You want to learn W in such a way that maximizes or minimizes something. What is that? The error. Minimizes the error. Or maximizes the?
correctness. Accuracy.
Accuracy.
Distance between it and the year's point.
Think about probability. Everything is in terms of probability right now. You want to maximize the
Probability that you're right.
the probability that you are right. How do you know your probability is right? Look at
Likelihood?
what?
Likelihood?
Look at the likelihood, exactly. Look at the likelihood of your data. because you want to improve your accuracy, you want to make sure you are right. How do you make that? You look at the training data, you see that whatever W you learned maximizes the likelihood, the way you see your evidence. That is the likelihood. Your likelihood is nothing but probability of X given Y. That is the likelihood. Any question? No? Okay. But there is a big question here. And we talked about what kind of likelihood? That's the question. Ideally, if your training data is like this, let's say x1, y1, x2, y2, x3, y3, n, yn. This is your training data, okay? What is the likelihood of this data with respect to the W that you want to learn? What is the likelihood? If you want to compute the likelihood function. Absolutely, but why a product? When you are making a product, what assumption you are making?
Independence.
Independence, okay? Okay, so let's come back. So the probability that you will see this data set is the likelihood. Simple. The probability that your training data will look like this is your likelihood function. If my W is such and such, what is the likelihood that I will see this? So you are saying what is the probability that you will see x1, y1, x2, y2 till xn, yn. Xn, yn given W. Given W. What is the probability that you will see all of them? But what is the problem with seeing all of them and computing this probability? If I want to compute this probability of everything together, estimating this probability is difficult. Why?
Big number.
What?
It's a big number.
Big number.
If
I mean, probability can only be as big as 1. Is that a big number?
if the probability of 1 is 0, then everything becomes 0.
Okay? I mean, there is no one thing, right? I mean, here you are considering this whole set together. What is the problem with this? Large data set. What is the problem with large data set?
We cannot find the probability together.
You cannot find the probability. Why?
Outliers.
Because
Takes from
because
takes too long.
too long. Or is it because every data set is unique? You have never seen this data set probably before. I mean, how do you even estimate a probability of a data set? Directly. And that's where you make an assumption. It's hard to see this entire data set. Maybe there are 2 copies at max. That is still like not a good way to estimate probability. So you make this assumption called IID. How many of you have heard this term? IID. What does it mean?
Independent, identically distributed.
Independent and identically distributed. What does that mean is, we're assuming that this data set, computing the overall probability of seeing this data set is hard. But if I assume something, that may make it easier. The product that you mentioned, right? So in order to make that product, in order to say that this is just a product of these individual probabilities, you need to make this assumption that this is IID, which essentially means these individual data points are independent of each other and each have an equal probability of being selected in the data set. So independent and identically distributed, the data set. If you make that assumption, then you can simplify your life. Then this number is essentially, this is your likelihood of the data, likelihood of the data set, and which is essentially a product over xi, yi, given w over I. Is that clear? And this is what we want to maximize. Why? Essentially, we are multiplying the probability that we will see xi together, given w, and we actually see they appear in the data set. So whatever w maximizes this is actually the right w, because you have evidence for them. This appears together in your training data set. That is your training. So you want to maximize this training data set, the probability of the training data set, each example of the training data set. Questions? Okay. So whatever w maximizes this function, this joint probability, is your right w. That's what we are trying to figure out now. Okay. And how do you maximize a function? Take the derivative, take a gradient, right? And that's why this formulation helps a lot. Now you can optimize with a theory, probabilistic theory. Okay. So let's see where we go if we want to maximize this. How my w should be learned if we want to maximize this likelihood function. So we will define the log likelihood, and the reason we want to have log is just to simplify our computation, because log doesn't change the trend of the function. It just makes it just transforms a function with the same order, but helps avoid underflow, overflow issues, right? So we will, because we are taking exponents, because this logit function has an exponent, working with log simplifies our life. That's the reason we are going to work with log. And yeah, so the log likelihood is with respect to w. Actually, that's how the notation is given. It's the data set, but yeah, likelihood is only with respect to w here because we are trying to learn w. That's the notation. It's nothing significant, but that's the likelihood function. So likelihood function was for each I, probability of xi, yi given w. And there is a log of that function. What is a problem with this? Estimating this, what is a problem? There is always a problem, right? Okay, what do we need to know in order to estimate this joint probability? P of xi together, xy together. What do we need to know to compute this? Yes.
The distributions of x and y.
Distributions of x and y, right? Because you need to know the probability of x and then probability of y given x for this, or vice versa. Probability of y, probability of x given y, right? Do we know this? In what kind of models we actually know this? What kind of models?
Batch data.
Batch data. Well, batch is an orthogonal direction, but we mentioned about two other cases. There was generative models, and there was discriminative models. Right? And we said, remember, which one was the generative model? Naive Bayes. Because we actually explicitly estimated these probabilities there. Right? How the data was generated. But for discriminative models, we said it doesn't care, and logistic regression is a discriminative model. It doesn't bother about learning this distribution of the data. It only cares about the final posterior that we actually want to compute. This. Remember? This is just by definition, because discriminative classifiers only focus on this. And we said originally this is hard to estimate because each data point is unique, and like defining a probability distribution over labels is not realistic. But we could transform the x to some other functions that might be easier to estimate this probability, right? That is what we are doing in logistic regression. We are replacing that with a logit of a dot product, and try to learn this function directly instead of looking at the distribution of the data itself. We are just interested in this posterior probability, the conditional probability of y given x. So, long story short is, for logistic regression, we don't know it yet. And we don't even, the more important thing is we don't care about that. The only thing that we care about in logistic regression, by definition of a discriminative classifier, is essentially probability of xi, yi given xi w. That's what we care about. So we don't want to maximize the original likelihood of the data. We want to maximize the conditional likelihood of y given x. Because this is a discriminative classifier, it's not a generative model. It doesn't care about it. Is that clear? Okay? All right. So, and then we need to define, so they are, okay, so my derivation here has an index over j, so I will just stick to that to make my life easier. Okay, xj, yj, j, j over j, and this j goes over 1 to number of data points n in your data set. So let's first see what this function looks like. So probability of yj equals to 1 given x, j, and w. How did we define this in logistic regression? What is this? You have it here, right? So that is essentially e to the power w naught. So let me go step by step. It was 1 divided by 1 plus e to the power minus z, where z is that dot product, right? Z is equals to w naught plus summation over wi xi. Can you tell me what is this xi, individual xi's? What are these?
Features,
Features of what?
the data,
Of the data. So these are individual attributes. For example, in the decision tree example, this is what is like a weather, xi. x1 is probably the weather. x2 is probably the humidity. Those values, right? But now it's continuous. If it is not continuous, we have to do something about it. We'll see, but right now it's continuous. So if we multiply, we can write it like this: e to the power z divided by 1 plus e to the power z. Right? I mean, multiplying with e to the power z in the numerator as well as the denominator. It's the same thing, right? Multiplying with e to the power z on both on the top and the bottom. Okay? What is probability of yj equals to 0 given x, j, and w? What is the value? Yes.
1 minus pyj equals
1 minus of this, right? 1 minus that. So 1 minus e to the power z divided by 1 plus e to the power z is essentially, you have 1 plus e to the power z minus e to the power z divided by 1 plus e to the power z. This cancels out. So this is the probability of y equals to 0. Clear? And we compute these two probabilities, and whichever is higher, we assign that label. But both of them sum to 1. So if it is greater than equals to 0.5, this must be less than 0.5. So you just need to compute 1 and make a decision, right? Think about this. What if z equals to 0? What is probability of yj equals to 1? If z equals to 0, what is this probability? What is the value of this? 50%. Because this is e to the power 0, 1. 1 plus 1 is equals to half. That is 50-50 probability that z equals to 0 or z equals to 1. Sorry, this should be, yeah, this is 0. This is probability of 1, right? Now, 0 should also be 0.5 because they sum to 1. So whenever your dot product is 0, your probability is 50-50. But if your dot product is a very high number, what happens? If your dot product is equals to positive infinity, what happens? What is this one? Why?
That's how
Right, because if you just look into this formula, if this is a very high number, that basically means e to the power minus, it's like 1 divided by positive infinity, which is equivalent to 0, right? So if this term cancels out, 1 by 1 is essentially 1. So if you have a positive number, probability of y equals to 1 and probability of y equals to 0 is equals to 0, almost, right? And it's vice versa for negative infinity. If it is negative infinity, then you have this as 0, this as 1. Just looking at this. Is this clear? Questions? Okay. Good. Now, we need to plug in, let's just get off with this n. Let's just go over like simple notation of over all the j. Okay? Yeah. So now we need to multiply all these terms, and the definition of this probability has how many cases? This probability, what should be the function for this? What should we replace? Can we just replace one function, or do we have two different cases we need to consider?
2.
Why 2?
When y is 1 and y is 0.
Right. You need to consider for cases where y j equals to 1, you need to replace with that function. Right? But if yj equals to 0, that function will look like this. So you need to have two different functions. But that's a little tricky. So that trick we are going to do is to write a single joint function that can handle that together with a multiplication. So the trick is you just write it this way. So e to the power z, and the log is also always there, 1 plus e to the power z, but multiply it with e to the power yj. Right? Yeah. I just want to make sure I'm doing the right one. Sorry, there is no, yes, so this is what I should do. There is no e, right? Times 1 divided by 1 plus e to the power z, 1 minus yj. Now look at this trick. What it is essentially doing, if yj equals to 1, this term will remain because yj equals to something to the power 1 is that. And this term vanishes because 1 minus 1 is 0, something to the power 0 is 1. Multiplying with 1 is essentially the original function. But if it is yj equals to 0, then this term vanishes because this is just 1 multiplied. But if this is 0, then 1 minus 0 is 1, and this term prevails, which is this term. So we are essentially handling both cases with a single function. Any question on this function? Okay? So it's essentially the conditional probability represented with one single function rather than two different cases. So far clear? Okay, now let's try to apply the log. And when you apply log on a multiplication, what happens? It becomes a sum, right? So now you have a sum over all the j's, log of this term plus log of this term, right? Log of this and log of this. So let me write it like this. And this derivation is already on canvas, so don't bother like writing every steps. I have already, so whatever I have here is on canvas, uploaded. Okay? And you'll have the video as well. So try to understand what's happening. Now, some log something to the power something, what happens? You can bring the power where? As a?
In front of the log.
Yes, in front of the log, right? So you can do a multiplication of yj, and you can do the same thing here. So you can do the same thing. 1 minus yj log 1 divided by 1 plus e to the power z. Yeah, don't need this bracket anymore. Something like this over all the j. Clear? And remember, this is still our log likelihood function. We are not into derivative yet. We haven't started the actual gradient computation yet. This is just the likelihood function we want to optimize. We are just simplifying it before we can compute a gradient, or we can take a differentiation, right? Question? Yes?
In the line above it, when we see the probability of yj given xj's w, like, what is yj? Like the probability of yj being what?
Is equals to 1 or 0.
Okay.
These are the two possibilities. This is your label. This is your target variable. This is a binary classification task.
So
yj can only be 1 or 0. So that's why we divided it into two possibilities, and we just tricked. We did some mathematical trick to represent them with a single function. Yes? Question?
what would that trick be called? 'Cause I don't think, what is
I don't exactly remember if it has a name, but the whole point is you have two cases with 1 and 0. There must be a name for this. Let me check. But what happens is this probability in case of this, when yj equals to 1, so you have this term, some term a multiply with yj plus, sorry, not the multiply, it's the power, right? One probability with yj, and the other case is 1 minus yj is the b. So the trick is essentially when yj equals to 1, that term vanishes. And when yj equals to 0, this term vanishes. It's like two cases you want to consider where the target is binary. You just want to consider one value for one case and the other value for the other case. But yeah, at least on top of my head, I don't remember any name for this. Okay? Now, what we do? We further simplify our life. Yj times. So we break it using log formula minus log 1 plus e to the power c plus 1 minus yj log 1 minus 1 minus yj log 1 plus e to the power z. Right? Just converting log division with subtraction of individual log terms. Right? Basic log formulas. Next, we can further simplify this. This term is essentially minus log 1 plus e to the power z plus yj log 1 plus e to the power z. This is coming from this term only. So we get rid of this. Simplification. Okay? We cannot do anything. Okay, we can do something about this. What is log e to the power z?
Z times log e times log e.
What is that? Just z, right? Log e to the power z is just z. So times z. We can we do something here? Okay, let's forget about this. What about this? What is log 1?
0.
0. Get rid of this. Right? Then what? one term is supposed to be cancelled because this yz has to be multiplied here, yj as well. I made a mistake. Sorry about this. Look at this term, yj log e to the power z minus yj log 1 plus e to the power z, right? This yj must also be multiplied with the second term. So now you can cancel these two out. Okay? So this cancels out. All you have is log 1 plus e to the power z. That is all you have. This multiplication looks like a x, so let me get rid of this. This looks simpler, right? Looks simpler.
Basically, the z minus log
What?
there, it will be just z minus log 1 plus ec, because yj once is 1 and the other time is 0. The summation.
I see. You mean when yj equals to 0, then this term becomes 0. When it is 1, it remains 1. Yes, I mean, that is true. But if we simplify this right now, so for positive cases, if it is actually z minus this. For negative cases, this is not z minus this, rather just this term. But then again, you cannot write a single formula for that, so, right? For the negative cases, it's just this. For the positive case, there is this z. So next, what we are going to do is now replace the original z function, which is a dot product, right? So w naught plus summation of I wi xi minus log of 1 plus e to the power w naught plus summation of I wi xi. Yeah. This is our final likelihood function. And this is what we want to optimize. This is what we want to maximize, right? We want to maximize the probability of the evidence we already have. We know this thing happened, and the probability that this thing should happen is this. So we should be maximizing this because we already know this happened, right? So now the question is what we should do in order to maximize this. What is our trick?
Take the derivative. And
Take derivatives, right? And because w is a vector, we take partial derivatives. It's a collection of numbers. You cannot just take derivative with one value. It has to be a partial derivative, right? So if we take a partial derivative of the likelihood function with respect to a particular w, let's say wk, we need to figure out what is going to happen with this, right? So let's look into this function. And let's say what happens to this term. Right. Yeah, look at this. What happens to this term? This time this. Taking a derivative with respect to wk, so the derivative with respect to wk, look at the first term, yj w naught. What is this value? 0. Why?
Constant.
It's a constant. Any other opinion? I mean, if this is the variable with respect to what we are like taking the differentiation, taking the derivative, I mean that variable doesn't exist here, so everything is constant here, and the derivative of a constant with respect to any variable is what? 0. So this is 0, the first term. Good. What about the second term? We still have the first term where the derivative was 0, but now try to multiply this with this, and what should be the derivative with respect to wk? Ykxk. Ykxk. Anybody here who doesn't see this? The derivative of this times this should be this. And we still have this summation over j that is outside. But for that term, we should have this. Any question on this? How many of you haven't understand this term? How many of you are exactly sure what this means? What about the others? So think about that term, right? Yj times I wi xi, which is essentially yj times w1 x1 w2 x2 wd xd, right? Now if you take a derivative with respect to, for this term, if you take a derivative, this with respect to, let's say, w2, what is this term? Derivative of this term with respect to w2?
0.
0. This one? Just x2. This term?
0.
Everything else?
0.
0. So x2 gets multiplied with yj. So xj multiplied with x2. This 2 is exactly our definition of k. So this has to be yjxk. My apology. Is that clear? Okay. Okay, let's look at the second term. We are taking a derivative of this term, and remember this yj is multiplied here. No, sorry, that yj is multiplied with the first term. Just take this term. Look at this term. And try to take a derivative of this. What is derivative of a log function? 1 by log. what is derivative of log x? 1 by x. So let's take the 1 by full log x, right? 1 plus e to the power w naught plus summation I wi xi, right? Is that it? Do we need to do anything else? The inner function, the chain rule, right? In a derivative, if you have a complex function of function, then after applying this, you need to apply the chain rule to actually find the actual derivative. So this is a complex function, so we need to also take a derivative with respect to e to the power that, right? What is the derivative of this function? What is the derivative of 1? 0. What is the derivative of e to the power x?
The exponent times e to the all that stuff.
Right, so I mean e to the power x derivative is e to the power x, and then you do again apply the chain rule, right? So e to the power this wixi, and then you are taking a derivative with respect to wk. So if you do that, you have the xk, right? I'm making sure I did the right thing. Yeah. Okay? So far good? But just look into this term. What is this actually? What?
The probability
Probability of yj equals to what?
1.
1. Right? This is our definition. Look at that function. E to the power z divided by 1 plus e to the power z. This is exactly the definition. So this is essentially saying sum over j yj xk minus xk times probability of yj equals to 1 given w and that should be the xk, right? Given xk. Just the definition we are replacing. Sorry, what? Because you are taking a derivative with respect to wk, right? And wk could be anything between 1 to d. I just didn't want to use I here because I is an index that is summing over all of them. I just want to make sure this is a particular I we are talking about, which is k. You could just replace I mean, it doesn't matter.
Here, it's k, like the probability of
This one.
yj, yes. xk, and I'm not sure why you can just put x instead of xk. Why not just x?
Because, well, sure. I mean, even if you put the particular x you are talking about, it's a summation over this, and you are looking at the probability of this given x and w, right? Now you are saying why this is xk, not just x. So look at this summation. So you have this summation over all the j's that you are doing. And you could also say for each xj, you need to sum over this, right? It's just about notations, right? You are considering each possible x over your data set. But the other variables, other than this kth attribute, is not going to impact this because you are taking a derivative with respect to this. So you could use a subscript and superscript like xj with k, because that is what is going to affect actually. You can also get rid of this as well in general. But this is, first of all, this x and w, all this is saying is with respect to x you are computing, but it is a summation over j. So it's a notational thing. That's what I want to say. So if you put xj, that essentially connects to each possible summation term. If you just say x, then you kind of implicitly figure out that for each example you are going to do this. So it's better to put xj here. And rather putting xk here essentially kind of implies the other values of xj indexes are not going to impact it. It's essentially the same thing. It's just a notational thing. Because other values are, if you take a derivative, they are going to go to 0 because only xk term remains. The other terms are 0. So this is essentially kind of highlighting that importance of that index. But it doesn't have to. You are right. You don't have to mention as long as you mention xj. Is that clear? I mean, j is the number of data sample, the data sample you are looking at. K is the attribute you are looking at. Now, if you are in a sum, both the attribute and the example number actually are important, because other than that particular attribute, no other attribute is going to make an impact. Now, if you want to explicitly show that in a notation or not, that's up to you. Okay? So now you can take xk common, and that becomes yj minus probability of yj equals to 1 given xjw. So this is how you want to update wk. Now is the interesting part. Now is the most interesting part. Remember, how did we update perceptron? And what is the difference between what we did for perceptron? So if you just follow this formula, what does this mean? This means wk in iteration t plus 1 should be wk in iteration t plus this term. This is how we are going to change it. J xk yj minus yj equals to 1 xjw. This is our update formula. What was the update formula for perceptron? What was wt plus 1? Equals to wt
Plus x or minus x.
and in a batch style it was a sum over the positive cases and a negation over the negative cases, right? So for the positive cases we added x for positive error. For negative error we did this perceptron. How is this different? Okay, how is this similar?
It's the same form, except you're considering more data points. Is that correct?
We are only doing update here if there is a mistake. Otherwise not, right? What are we doing here?
You're updating by how wrong you were on each.
Right. So think about this. This term is getting updated with the exact xk. And this is here the x, right? I mean, this is just a partial derivative. That's why we have the k. But we are going to do that for all k's. But the point is, whether we are adding or subtracting here, that addition term is also here. And we are adding over all the possible examples. So that part is exactly the same. What is changing is this term, this part. We have a probabilistic term in the second part that we are multiplying with x. Here, if I say there is an alpha with x, what is that alpha? What is the value of alpha here? What is the weight we are putting on x? What is alpha? Come on, this is 1, right? I mean, this x, you are adding whole of x, the totality of x. You see the point? Here, you are not going to add the full amount, full value of x. You see the difference in learning between logistic regression and perceptron. If you make a mistake on a particular example, add that whole example. Don't care about updating your weight, because think about this. You have made a mistake for this example that is close to boundary versus you have made a mistake here. Right? You don't care how much mistake you have made, you just add them. But here, you discount x with some value with respect to how much error you are making. How? What is yj? Yj is the actual label. And what is probability of yj given xj? What is this? But what does this mean? Is this a ground truth? Is this the label?
The probability.
No, it's my prediction. It's the model's prediction that how likely this xj is 1. The label is 1. So this is, what is the actual label? Minus how likely I think is the label. The model thinks that the label is this. So think about two cases. If yj equals to 1, and the model also thinks that it should be 1, probability equals to 1, then 1 minus 1 equals to what? 0. 0 times xk is what? 0. Don't do anything. This is exactly what perceptron said. If there is no mistake, don't do anything. Is that clear? If yj equals to 0, and we are also predicting that yj equals to 1 should be 0, because if yj equals to 0, then yj equals to 1 should also be 0. If we are predicting correct, then this is also 0, multiply with 0, don't do anything. So as long as you are correct, predicting 1 as 1 and predicting 0 as 0, you are good. Things get tricky when you think the opposite. For example, yj equals to 1, but your model predicts that the label should be exactly 0. That means your model is wrong, maximally wrong, right? For that example, your model is maximally wrong, so 1 minus 0 becomes 1. In that case, you add the totality of x, xk times 1. That example, you are making a drastic error, so you add the full x. So it's basically saying, previously, it doesn't matter how wrong you were, the updates would be exactly x. Every point makes equal weights. But here you have different weights based on the error you are making. If you are making more error on a data point, you will adjust more. The W will shift more because this point is making a huge mistake. I'm making a kind of opposite prediction for this model, so I'm making huge error on this. So the amount of correction I need to make is huge. Versus I made a small error. Maybe the difference is I predicted to be 98% and here it predicted to be 96%. So the amount I still will change, but very little. It's not a big deal. I'm still somewhat correct. Is this clear? I'm not convinced with the amount of head nodding I'm seeing. Okay. Yeah, it's a little messy math. Go back to your home. Look at the draft I have. This is uploaded on Canvas. Do the derivation by yourself. And then convince yourself, come to the next class saying, I understand this. Because don't tell me you don't understand, because I have to go over that again. I don't want to. Yes?
So the formula kind of implies that you have to compute the gradient over all of the batch at once. Could you instead do it like item by item and just...
That's a very good question. So the point is, it looks like a batch style learning, right? Because you are summing over all the instances of J and then it basically is a batch learning. Can we do it like a online fashion that we did initially for perceptron? We showed like perceptron is an online algorithm and then showed that it will also work in batch. Here we are showing in batch, and then there is also a proof that it also works in the online fashion in the similar way. So you could just, this is a gradient descent, but there is a stochastic gradient descent version where you don't do it for like all the batch together. You take one example, you just update with respect to that example, and just keep doing this. And there is theoretical proof that that will converge as well. Yeah, good question. So both logistic regression, perceptron are the same thing. Batch algorithm works. The online algorithm works. It is just a logic transformation on the perceptron that allows you to apply all the theories of probability. Now you have a probabilistic model that you didn't have before. And now you can account for the amount of error in terms of the probability you're making, because previously quantifying the error was hard because you didn't have a bound for the points themselves, right? The amount you add and how much you could add and how much you should discount. Now you have that technique. Okay? All right. We'll revisit this and we'll go over, briefly review this derivation again in the next class, but you need to do your homework first to go over the derivation as well. Thank you very much.